This is a presentation of an approach by a paper Optimal Action Extraction for Random Forests and Boosted Trees by XAI et al. From Washington University in St. Louis in 2015. This presentation talks about counterfactuals for classification. That is, if we have a classification task like do I sell my apartment and we don't sell it, then what is the smallest change or change combination to my apartment's features that I have to make in order for it to get sold? In machine learning, data science tasks that are basic, which we all the time will end up solving, are, for instance, twofold: regression and classification. In your credit scoring world, the regression tasks are your loss given default problems, and classification tasks are your probability of default tasks. The two most successful approaches of how these are getting solved in machine learning world are artificial neural networks, ANNs, and decision tree based approaches. In this presentation we talk about machine learning task classification, and we tackle it with decision tree based approaches. So out of the four options, those two are being selected. In order to put everyone on the same page, let's see what a regression and classification tasks are like, and then proceed to a specific example. For regression, we could ask, what is the temperature outside of my apartment? And if we use a decision tree 1 here to analyze this problem, then, and our features are, our four features in question are valued at 1, 4, 5, and 6, then this decision tree at first looks at the first feature and checks whether its value is above 2.5. And we can see that it's being 1, it's not, so the decision tree branches to the left branch. Then it looks at the third feature and checks whether its value is above 28. And again, the value isn't above 28, so it branches to the left branch. And if we tackle the decision regression, the temperature regression problem with this first tree, then the regression value outputted by the tree is minus 0.009, which is the answer. Considering the same decision tree and the same decision, it's important to see, as we were looking at features 1 and 3 here, in the space of those features, the decision tree, while it's making its decision, is doing a 90-degree cut in the first case in the feature 1, and then nextly in feature 3, and then selects the pertinent region and outputs minus 0.009 for all this region, given our data point is here. And this is what the decision trees generally tend to do. The decision tree could be more complex, but it always does cuts like this: below 2.5, below 28, above 1.2, above 26. And it always does 90-degree cuts in the space and then outputs a value. And this is a more complex tree which did this decision. You can see the output value here is plus 0.009, and the decision trees with varying depths always do those 90-degree cuts. Whereas for regression we were considering continuous values as outputs. For classification the output will be 0 or 1. We now switch with the example of the same tree to a task of classification. The feature values 1, 4, 5, 6 will be the same coincidingly. And we want to see whether this apartment, now the 1, 4, 5, 6 are apartments parameters in this problem, whether this apartment will get sold or not. We will use a forest for that. There are 10 trees. The first tree is the same one we saw, so given the 1, 4, 5, 6 it outputs the leaf minus 0.009. And there are 9 more trees, second, third, fourth, and so on. You can see that the trees have varying depths. So the first tree has 2 levels of branches, the third tree only 1. It considers different features, like the first tree considers first and third feature, the fourth tree, second and third feature. And as we run the given apartment with feature values again 1, 4, 5, 6 through those trees, we get these leaves as outputs. This is an unlucky coincidence that it always chooses for this example the first leaf, as you can see, of the tree. It doesn't have to be this way, but now let's see how the classification result will be outputted. We take the leaves that have been selected and we line them up and sum them up. So the sum of the selected leaves is minus 0.207. And in order to, and if it was regression, this would be the answer. But for classification, what we need to do is to run this through a sigmoid function. Sigmoid function at its x-axis has this sum that we have just calculated, and at x equals 0, the sigmoid would output 0.5. So here we see that the value is just below 0. And the output will be somewhere below 0.5, 0.448, which is now where we will apply a threshold 0.5 for classification and see that since it's below 50%, and this would be our chance of the apartment being sold, then the final result is no, the apartment will not be sold. And we will now come to the central question of this presentation, namely, since this apartment is not getting sold, what is the smallest change to the parameters of this apartment or the properties of this apartment when it comes to real life that we would have to make in order for it to get sold? This is essentially an XAI, or explainable artificial intelligence question. And let's tackle it now with by crunching an integer linear programming ILP problem put forth here. We will go through this problem equation by equation, but let us at first say a few words about the little toy problem that we have solved here. This problem, while training the model, had only 3 apartments. The features were 1, 4, 5, 1, 4, 5, 6 for the first apartment with class being 0, 4, 5, 6, 7 for the second with the class being 0, and so forth. The third apartment was the one which got sold. So this is how we trained our forest with 10 trees. For this particular problem, the integer linear problem that we set up will have about 40 constraints and 40 binary variables that we'll see in detail later. However, in real life problems, there could be, for instance, for something we've looked at 1,200 trees or so and 150 features, which means that the problem will have 40,000 constraints and 40,000 binary variables and 40 million coefficients to be optimized. So it's going to take a powerful solver to crunch through it. Let's at first look at the objective function of the problem, the first equation, and we notice that there are decision variables Vij, and depending on the features of the apartment, a function Cij, which creates a distance matrix based on it. Let's see how this in a detailed way plays out. We have 4 features for this particular apartment, and as we look at feature 1 and the entire forest, let's note the places where feature 1 is at hand. We see that it's only in the first tree, and the value that is being looked at is 2.5 or above. So what we do now is we bin the first feature from 2.5, so the first bin will be minus infinity to 2.5 included, and the second bin will be above 2.5 to plus infinity. So this is how, for the purposes of this problem, we bin the first feature. Let's now bin the second feature. We look at the forest values which deal with the second feature, and we see that although it's been tackled many times, the values, if you look at through all the red circles, are just at 4.5 or 22.5, which means that we bin again the second feature. And just one more example, minus infinity to 4.5, above 4.5 to 22.5, and above 22.5 to plus infinity, which gives us the free bins for the second feature. Now we do the same exercise for the third feature and end up with similar bins. And when we look at the fourth feature, it's been used just in two places, but it gives us also bins, 3 different bins, from minus infinity to 6.5, above 6.5 to 33.5, and above 33.5. So we see that we have binned the features into 11 different bins for those 4 different features. Coming back to the objective function, Vij are binary variables pertaining to those 11 bins. Let's see what Cij now is, the function of xc. When we look at the objective function for the class 0, meaning that if we take our apartment, run it through the integer linear programming problem, and predict and see for class 0, meaning that what would be the changes that we would have to make in order for the class to be predicted 0. Then of course we don't have to make any changes because the class already was predicted to be 0. Meaning that in that case, the Vij, the 0, 1 variables, would select this bin here, as 0 changes are belonging to this bin. When we in order to give an understanding of Cij, the function of xc, we now take the final result, the counterfactual solution, jump to it right away, which says that if the class was to be 1 for our apartment, we would have to make the smallest following changes to the features of the apartment. The first feature doesn't have to be changed at all, so this is okay, and this remains in this bin safely. But the second feature the third feature has to be changed from 5 to above 5.5, and the fourth feature has to be changed from 6 to above 6.5. So there is some change that has to be made to the apartment's condition, and the second feature has to be changed the most, from 4 to above 22.5. And these changes will shift the active bins to those constellations and retain the first in the current state. So this is the counterfactual solution and the Vij values for. Once again, in order to understand Cij, let's now look at what the lowest limits to the changes made in order to arrive at the counterfactual solution were. So the first feature didn't have to be changed. The second had to be changed by at least 18.5, meaning that from 4 to 22.5 over 1, at least such distance has to be taken. The third by at least 0.5, and the fourth by at least 0.5. So what Cij is about is exactly this matrix of distances, meaning that, for instance, if our change to the second feature would not be from 4 to 22.5, but from 4 to 4.5, rather 4.501 because the bin starts from above 4.5. Then this feature would have to be changed again by 0.5 at least, or at least by more than 0.5 to be very exact. So this distance matrix is Cij, and we couple it, multiplying it one by Vij, the decision matrix regarding the bins that have been on switched for different features. Well, Vij is this matrix, Cij is this distance matrix. Let's now take turns going through the equations of the problem. The third equation, depicted here, just says that for Vij, it's a constraint on Vij, one bin gets selected for each feature, meaning that the solution that we look at here for the final counterfactual solution already satisfies this constraint, but exactly in each column just one selected bin will have to rely. Next up is, in the second equation, phi tk. Phi tk is in the forest, the question whether the kth leaf of the tree number t is turned on. So for instance, for the first tree, the first leaf is turned on. For the fourth tree, the first leaf is turned on. And it's been solved for all the trees and all the k leaves. 10 trees, 30 leaves if you count them all together. Let's now look at the equation number 5. This is solely about phi tk. It says that one leaf gets activated on each tree, meaning that if you fix a tree, t equals 1, and sum it over until the leaf number, which is 4 leaves, then only one and only one, will be selected. Let's now look at the constraint number 1, or the second equation, and while we look at its value, it's essentially the calculation of the forest result. Meaning that it takes htk, and htk is the value of each leaf that is being outputted by the tree. So you can see it sums over all the trees and all the leaves, so htk is really all the leaves outputs. It multiplies by phi tk, meaning the leaves that are being selected. Meaning that since phi tk in the problem is a binary variable, as you can see, it just selects those leaves outputs that are being outputted by the respective tree. The final weight for weighing catpuss trees, as here, is equal to 1 for catpuss trees. And as we look at the output calculation, which we saw at an animated slide before, this value will have to be above z. You notice that there is no sigmoid function in this value, in this constraint. So if sigmoid function had to be above 0.5, then this means that z respectively is 0, because for sigmoid's input above 0, the sigmoid's output would be above 0.5. Having gone over almost all the equations, we now finalize with the last, the most complex one, which ties together features selecting each feature just one bin, and the trees of the leaves. Each tree outputs just one leaf. Let's look at the intuition of the topic. Let's now look at the tree number 4 for the given counterfactual solution. The tree we'll look at feature number 2 and see that 22.501 is above 4.5 and branch here. The tree will then look at the feature number 3 and see that 5.001 is not above 28 and branch here, selecting leaf number 3. We have herewith given the v, I, j variables explicit numbers. For feature 2, v has v21, v22 and v23. For feature 3, v has v31, v32 and v33. When we look at this third leaf of the fourth tree, and as this constraint evolves, it takes all the leaves of all the trees. But if we look at this particular leaf, we are going to be looking at all its ancestors, meaning the green branch and the red branch. And at each ancestor, we look at into which direction we want to go and which v variables lead to that direction. Meaning that, for instance, here for feature 2, if we want to go above 4.5, we have to select either this v22 bin or v23 bin. And for feature 3, if we want to be below 28, we have to select either this v31 or v32 bin. You see, they're depicted here. And if we want to go for feature 2 to the other direction, then we have to select v21. And if we want to go to the other direction with feature 3, we have to select v33 here. So this is where we have to go, what we have to select given where we want to go. Remember that we're working our way backwards from the solution. So this is the counterfactual solution. And we can see that we really do end up in this leaf because v23 here and v32 here have really been switched on in the counterfactual solution. So the tree will really branch to this leaf. But now let's look at one other leaf, for instance the first leaf. You see that the value of the second feature has to be less than 4.5, leading only to the direction of v21. And the value of the third feature will have to be less than 28, which leads to the direction of v31 and v32 here and here. So you see that although the second level branch would branch the right way, the first level branch doesn't. Thus, this leaf is not being outputted by this tree. To sum the fourth constraint up, we see that for each leaf, the tree's leaf is switched on only if the sum here, which takes for each ancestor each respective bin that could be turned on, and then those bins that are really turned on will give such a sum that it will let the leaf be turned on. The reason for the division in denominator is that the denominator takes the set of all ancestors, here the red and green, and looks at how many there are, namely 2, and by the virtue that each feature only has one bin switched on, then this sum will also be in the numerator will be 2 in case this leaf for the given tree is switched on. So it's gonna be 2 divided by 2, enabling the switching on of the respective leaf. In conclusion, we can say that the method converged on a counterfactual solution whereby the smallest change combination that one has to make to the properties or features of the apartment in order for it to get sold was identified. The tree calculation was introduced as a constraint, which meant that the apartment will have to be sold. The objective was minimized to a value above 19.5 for the features that had previously been normalized in such a way that all the trees of the forest would produce an output and all the features would have a bin turned on. We're effectively looking for, so to say, cheapest change to the apartment that we would have to make in order to reverse the market's decision. Anything else would be an overkill. The amount of combination that has to be looked through is astronomical.